The TI-9900 is an incredibly interesting home computer. It still, to this day, gets lambasted for being woefully underpowered, but the truth is that there's actually some legitimate power lurking underneath the skin here. So why is it so slow? Well, there's a lot of elements of the design that were massive compromises that really hamstrung it. But if you knew the right incantations, you could get it to do some pretty tricky stuff. Right now, I have it sitting here calculating this beautiful fractal program. And this is running on just a pure vanilla TI-99. Just the stock base 16K of DRAM and the built-in TI Basic. I found this program over on the Atari Age forums, written by sometimes 99er, and I think this is a beautiful demonstration program. One of the reasons that I really love the TI-99 is because it has such a powerful processor hiding out in it. This was the first 16-bit home computer. Granted, the 16-bit CPU was shoehorned into an 8-bit design, and then all of the memory was locked behind the video display processor, but that CPU is properly awesome because it's a large-scale integrated version of the TI-990 mini computer CPU. And that is this beautiful thing, the TMS9900. I have a white and gold ceramic package as well as a plastic dip package here. We're doing all of our testing on the plastic dip package, but the finalized version will use the white ceramic. It has so many pins on it because you have the full 16-bit data bus and 15-bit address bus. Now, it sounds weird to say 15-bit address bus because this thing can access 64 kilobytes of memory, but it can only access that one word at a time. So you only get 32 kilowords, which is 15 bits of address space. Now, there are some pretty quirky things about this CPU that we're going to have to work our way around. Notably, there's not really any registers on it. There's the program counter, the workspace pointer, and a status register, and that's it. So where are all the general purpose registers that a programmer is going to need access to if they're going to write software for this CPU? Well, they're all in RAM, which seems like a choice, but actually this unlocks some pretty awesome capability. Because this is a mini computer CPU, multi-user capability was a top tier feature that it needed to have. And by putting all of the CPU registers in RAM, you can have multiple copies of those registers. So you can have multiple users with their own set of CPU registers, and you can jump back and forth between those incredibly rapidly. This is one of the main driving forces behind why I chose this CPU. I think this functionality is absolutely awesome. Although, if I'm being honest, the primary reason that I chose this CPU is because this golden ceramic package one is just so gorgeous. I really wanted to use this in something. So in the previous episode, we ended up building two cards here. One of them holds the CPU and the other one holds the TI-9900 that generates the special 4-phase clock that the CPU needs. Now, you guys saw these boards and left some interesting comments in the previous episode, so let's address those right quick, starting with the CPU board here. A lot of y'all had opinions about my PCB construction technique here, going so far as to say that this is all a massive waste of my time and it'll never work, and who knows, y'all may be right, but there's only one way to find out, and that's by doing it. But the reason that I'm building the PCBs like this is that I'm machining them myself on the Bridgeport mill here, which is a construction technique that I thoroughly enjoy doing. This is a hobby, and hobbies are meant to be enjoyed, and I enjoy doing it this way, so that's the way I'm gonna do it. Now, a lot of other people left comments concerned that I didn't have enough decoupling capacitance on the power rails for the CPU. And I could see where that concern could come from because I actually hid two decoupling capacitors under the CPU itself, so you may not have been able to see them. But don't worry, they're in there, they're just hidden from sight. And over here on the clock board, I got a lot of people asking questions about why I decided to use wire wrapping to set my jumpers for pull-ups or pull-downs. It would have been way easier to actually just use connectors that I could connect and disconnect. But the truth is that I just wanted to do some wire wrapping. I think it's a ton of fun to wire wrap individual pins, and This was just a design choice that I made because I thought it was fun. Now there is a fatal flaw on this clock board that some of y'all pointed out, and that is that it is running too slow. In the TI documentation for the TMS9900, it just talks about the clock speed as being 3 megahertz. I incorrectly thought that this meant that the CPU could be run at any speed up to 3 megahertz, and I wanted to run this one at 1 megahertz. However, a lot of people chimed in the previous episode and let me know that that may not actually work. And so I started doing some hunting around, and legitimately, I can't find anything official from TI that says it can run at anything less than 3 megahertz. However, this particular plastic package, TMS9900, is built by AMI. And AMI did release a datasheet for this chip, and in there they do list a minimum clock speed. They say it can be from 0.3 microseconds to 0.5 microseconds. So this particular one can run as low as 2 megahertz, but I have no idea if this gold ceramic package one can actually go that low. The official TMS9900 from TI may be locked in at 3 megahertz. So this clock board that we built here, which is ticking along at 1 megahertz, is not going to work. So in order to update this, all I got to do is desolder this crystal oscillator, this inductor, and this capacitors. And I'll pop in the appropriate ones, and then we'll be chugging along at 3 megahertz. When we hit reset by pulling the reset line on the CPU temporarily low, it immediately jumps to memory address 0000, and that is the reset vector where it does some pretty interesting things. And we can figure that out by looking at our 9900 family systems design tome of knowledge here. If we go to page 4-13 here, we can see the memory organization, and memory address 0000 and 0002 is the level 0 interrupt, also known as the reset vector. If we jump over to the next page, we can see it says the reset vector is used to load the new workspace pointer and program counter whenever the CPU reset signal occurs. So when we reset that CPU, it jumps to this location in memory, copies the value into the workspace pointer so we know which collection of registers we're working on, and copies the next value into the program counter, which it'll then jump to and start executing code from there. If we go back to the previous page, we can see that after the reset vector is a whole bunch of interrupt vectors, and then we have a bunch of software trap vectors all the way up to 007E, and then we get into the general memory for program, data, and workspace registers. Now the memory from 0080 on is really flexible. We can make this read-only memory so that we do specific things when we get to those locations in the memory address, or we can make this random access memory so we can temporarily store things and change them there. We have a lot of flexibility. This is also where all of the CPU registers are going to live. So we need to set aside a little block of space for that. And now things are starting to get a little confusing. Where is our read-only memory going to live? Where is our random access memory going to live? And this is something that we got to kind of sit down and figure out. And so that's kind of what I've been doing. I sat down and tried to make a memory map that made sense. The general memory starts from 0080 and up to 0FFE, I'm going to place what I'm calling the console ROMs. This is going to be 2 kilowords or 4 kilobytes, and I'm going to build that out using these 2 little ROMs right here. These are 27C16 EEPROMs. There's only one E on that, which means that they are erasable via a UV light on the little window on the front. I think these just look really beautiful. That's why I want to use them. But I think for rapid prototyping, we're actually going to use these 2 little XL ROMs here. These are XLS28C16. I believe these are pin compatible with these 27C16s over here, but these are EEPROMs, 2 E's, which means that they are electronically erasable. So I can very rapidly change the code on these. Now, once we go beyond our ROM location here, we're going to get into register RAM. This is going to be some fast static RAMs that hold all of the CPU registers and local memory like that. And then we get into general RAM, and then finally we get into what I'm deeming the MMIO space. This is a space of 126 words where I can hit a specific memory address and get an IO device to do something. We're going to lean pretty heavily on this when we get to getting a data terminal hooked up to this, because I'm going to do all that via MMIO because it's way easier. easier to do it that way. But today we're pretty much only concerned with the console ROMs. So I've got these two ROMs. How do I get them to interface with the CPU? Well, in our little book here, if we shuffle on along down to a much later page, when a basic read cycle is happening, mem enable goes active low during each memory cycle. At the same time that mem-n is active, the memory address appears on the address bus bits A0 through A14. So this is the point at which the ROMs need to start listening to that address bus. If the cycle is a memory read cycle, dbin will go active high. At the same time, mem-n and A0 through A14 become valid. So there we go. There's the two signals that we need to pay attention to tell the ROMs, hey, it's time to put some values on the data bus. Mem-n, which is active low, and dbin, which is active high. So we need a collection of logic to control those, and I've got that kind of laid out right here. Essentially, if any of the address bits A12 through A15 go high, this is outside of the ROM space, so we want to keep the ROMs squarely turned off. Now, data bus in is going through a spare NAND gate to invert it, and that is being ORed with mem enable. This is going to go into this collection of NAND gates here, which is controlling the output enable line of the ROMs. And so when the output enable line is low, the ROMs are going to output their value, and when it's high, they're not. They're going to be silent on the bus. So we just need to implement this little bit of logic and wire up the two ROMs here to our data bus and our memory address bus. And I've actually already gone through and made some schematics for that and designed it out. Now I have added a couple extra 555 timers in the mix here, and this is just to handle the reset signal. So that way we have a little bit of power on reset and a button that whenever you push it, it resets the system. And because I'm a bit proactive here, I've actually already made the PCBs. I fired up the mill, we got to work cutting these guys out. They cut out beautifully well. So all that's left now is to solder these up, put the ICs in them, plug them into the backplane, and see if we can get the CPU starting to execute some instructions. Through the magic of hours of work off camera, both boards are now fully soldered up and they look absolutely awesome. This one is by far the simpler one. It just has the two ROMs on it for high byte and low byte. This one has a little more going on. We have our output enable selection going on here that's going to pass through one of these pins along the backplane over to the ROMs. And then we have our power on reset and a little reset button here that's going through the monostable multi-vibrator. And we have a little run LED up here. This is our very first blinking light. That should be on whenever the system is running and off whenever reset is asserted. Now, I haven't plugged these in and smoke tested them yet because, well, we need to figure out what program goes on these ROMs first. Whenever you hit reset, it goes to memory address 0000. It grabs that value, stuffs it into the workspace pointers, and then it goes to the memory address 0002, grabs that value, stuffs it into the program counter, and jumps to that location to start executing code. Now, all of our registers are going to be in RAM, and that's going to be starting at memory address 1000. So that's the first value that we need to put in. Then I want our actual program to live at memory address hex 80, and that's where essentially the core software of the machine is going to live. And, well, now we have a bit of a problem. Even if we're running core software, like, we don't have any RAM, so there's not a whole lot that we can do, and we don't even have any input-output. So even if the program was successfully running, we would have no way of knowing. Except there's one thing that we can do without any RAM, and that's an unconditional jump. And if we do an unconditional jump to very specific locations in memory, we should be able to see the memory address lines twiddle a little bit. So I wrote a program here that says at memory address 80, we're going to jump 7 words forward, which is going to put us at memory address 90. And then at that memory address, we're going to jump another 7 words forward, which should put us at memory address A0. And then we're going to jump 16 words forward, which should put us at address C0. And then finally, we jump a bunch of words backwards down to memory address 80, and we're just going to run this on infinite loop. So why did I choose these specific memory addresses to do unconditional jumps to? Well, if we look at the actual binary of these memory addresses, bit 7 should always be set, but bit 4, 5, and 6 should be set in sequential order without ever overlapping each other. So we go 1001, 1010, 1100. So we should be able to put a scope on those three memory address bits and see them toggle sequentially without ever overlapping. But we got to take this jump 07, jump 07, jump 0F, jump DF. We got to take all of that and somehow get that onto the ROM. So we need to assemble the program into machine code. Now there are some tools out there, but I did this one by hand because I felt it was important to learn how assembly worked on the TMS9900 here. At 0000 and 0002, that's pretty easy. We just write 10000080. When we get to memory address 0080, the jump command, if we look in our little book, is hex 10. And then you write in the displacement after that. And our displacement is 07. We're going to do that again at 90, 1007. And then at A0, it's going to be 100F. And then at C0, it's going to be 10DF. And I actually wrote out the entire machine code here, but this is assuming words, and our ROMs won't do words. So we need to split this up into high byte and low byte. Now I just did that by hand because this is such a short, simple program, but once the programs are much longer, it's going to be much more difficult. Now I've got these written to the ROMs on here. So let's go ahead and plug this into the backplane, and then we'll get the scope hooked up to it, and we should be able to see what's going on. All right, first proper power test with the ROMs in place and the power on reset circuitry going on. Hopefully nothing goes up in smoke. What I am hoping to see is this little red LED stay off for a, I don't know, about a second or so, and then come on to tell us that, well, reset is no longer being asserted and the CPU is running. So let's go ahead and flip the power switch. The red LED came on. If I push the reset button, it reset. Oh, there it goes. That's like an incredibly long reset. Maybe I need to rethink some stuff here. No, that seems a little more consistent now. I have no idea why it was so long the first time. My power on reset circuitry may need a little help, but for the moment it appears to actually be running. Okay, I've got the scope hooked up here. The yellow trace here on the bottom is going to be the clock because we upgraded that to run at 3 megahertz. So I want to see if that's truly chugging away at 3 megahertz. Then we have the 3 address lines that should be toggling with our program. Now I'm not expecting this thing to just work right out of the gate. I'm never that lucky, and I built it, so I know that there's going to be something wrong here. But let's go ahead and flip the power switch on and at least see what's wrong. Boy, that's wildly different looking than I was expecting. It looks like I've got some settings wrong here. Let's see here. You're on, there we go, 10x. Okay. It doesn't look like our clock is going on. We should be triggering off of the clock here, and it doesn't seem like we are. Right, I forgot about this. This is a problem from last time. The clock doesn't extend to this front header that I've got all this stuff plugged into. Everything else does, but the clock doesn't, because I don't know. So we're just gonna unplug it from there. I'm gonna plug in this little connector here, and we're gonna go to pin 8 of the CPU. So 1, 2, 3, 4, 5, 6, 7, 8. Right there, that should be Phi 1. So now we're hoping to actually trigger off of that and see that on the scope. All right, let's try this again. I'll go ahead and turn it on. Definitely looks like we're triggering on it now. That clock is booking fast. Let's see here, let's take a measurement of that. Yeah, dead square at 3.001 megahertz. That means that our clock is working perfectly. Okay, that's great. Now let's see if our address lines here are twiddling like we're kind of hoping them to. And we're gonna do that by changing our trigger to source 2 here. Hopefully we should start triggering on that one. And nope, dang. That is absolutely not doing what I wanted it to do. Let's get the clock out of the way there. I was expecting to see each one of these toggle without overlapping another one, but it looks like we're just pushing straight through. The program counter is just incrementing normal without actually reading or executing any instructions. Okay, I got something horrifically wrong because I pulled these ROMs out to see that maybe I had them backwards, and they are meltingly hot. They've been out for a little while now and they're cooling off, but you can see that they're sitting at 40 Celsius, 38 Celsius, 39 Celsius. That's after cooling down. When I first pulled them out, they were burning my skin. So clearly I have some power routed wrongly. We may have destroyed these ROMs, which is unfortunate. So here's the problem. The VCC pin on both of these ROMs is supposed to be tied to 5 volts, but if I check it with my multimeter, it is connected up to negative 5 volts. So both of these ROMs may be damaged, but how did this happen? How did I get negative 5 volts and plus 5 volts backwards? That should have shown up as an error when I was laying out the PCB. Well, I kind of laid out all 4 of the PCBs, CPU, clock, and both of the ROM boards at the same time. And about midway through, I decided to switch the position of minus 5 volt and plus 5 volt. It made the routing a lot simpler for some of the boards. And I went through and I thought I updated all of the boards with the new layout, but it seems that I forgot to update this board only with the new layout. Not a design rule problem, a human problem. I'm gonna slice this trace down here on the bottom and run it over to the right one. All right, little bodge wire in place. So 5 volts is now going to VCC as opposed to negative 5 volts. I did pull both of the ROMs out and check them in my programmer, and they both read back fine. So hopefully we didn't injure them too much. I'm still not expecting this to work perfectly, but I don't know. Here goes. Let's flip the switch. Yeah, not what I was hoping to see. Looks like we're not triggering on source 2 here. Looks like source 2 is not doing anything. I can see that the blue trace and the purple trace are doing something. So let's go ahead and flip the trigger over to that. And oh, I mean, look at that. That's kind of what I wanted to see. It looks like those 2 memory address lines are toggling, but they're never overlapping. So the question is why is this memory address line not toggling? Yeah, looks like I counted incorrectly here. I think I'm off by 1 pin. So we're going to scoot all of these down by 1 here. All right. There we go. That should now do what we're expecting it to do. And here we go. Power coming up. Yes! Check that out. That's exactly what we wanted to see. We can see that each address goes high and then low sequentially, and they never overlap. The CPU is executing jumps to the correct locations, and it's doing it perfectly. We are running real deal code on our Homebrew. Here we are chugging along at 3 megahertz executing code. It is doing unconditional jumps to specific locations in memory on a tight repeat. It works. And this is not a scope shot. This is live. If I hit the reset switch here, that's all gonna go dead until my little red LED comes back on, and we should have little squiggles on the scope right now. Like this is, at least I hope we do. Yeah, okay, we got our squiggles back. This thing is sitting here, chugging along in a tight loop, executing code that we programmed on some ROMs that we dramatically overheated, but it's fully working. So the next up, we're gonna build some RAM into this. And once we have RAM there, we now have all the CPU registers, we have working memory, we can start doing some really tricky stuff. Of course, we still can't get it out to the user. We gotta figure out some IO as well. So after RAM, then we're gonna build a UART, and then we can get into some really fun stuff by plugging in a data terminal. This is really cool. It's executing code. It's executing a program that I wrote. Like, this computer is running a program. That's cool. So I wanna thank you all so much for watching, and I hope to see you in the next one.